Okay, let's unpack this. Today, we're diving deep into one of the really compelling frontiers of artificial intelligence. How AI doesn't just play games, but how it truly masters them, especially, when it's facing an opponent who's actively trying to win.
Right, an adversary. That's the key difference.
Exactly. So our mission for this deep dive is to explore these core concepts of adversarial AI, pull out some key insights, and maybe spot some surprising patterns in the strategies AI uses.
And maybe challenge what we think optimal play even means.
Yes, precisely. We're drawing from this really fascinating academic briefing on adversarial search and game theory. It's packed with fundamentals, history.
It really sets the stage well.
It does. And get ready for some aha moments, because what these docs reveal about AI tackling chess, Go, even poker, it's kind of mind-bending.
Definitely.
So let's start right at the beginning. How does an AI even start thinking about a world with other agents, especially agents who might be, well, working against it?
Yeah, the sources lay out 3 basic stances an AI can take. The first one is really for huge numbers of agents. You just view them in aggregate, like an economist predicting market demand. Right. You don't model every single person.
You just see the overall trend.
Exactly. The second stance treats adversaries as just, well, part of the environment's uncertainty.
Yeah.
Like random weather.
Unpredictable rain.
Yeah, right. But crucially, that stance misses something important. As the source says, it misses the idea that our adversaries are actively trying to defeat us, whereas the rain supposedly has no such intention.
Ah, the intent. The rain isn't out to get my picnic.
Precisely. Your opponent is.
And that leads us to the third stance, which is our main focus, right?
Yes. Explicitly modeling the adversarial agents using game tree search, trying to predict their moves, their goals.
Getting inside the opponent's head, so to speak.
In a computational way, yes.
So when we talk about AI mastering these classic games, we often start with a specific type, don't we?
We do. The foundation is usually deterministic, 2-player, turn-taking, perfect information, zero-sum games.
Okay, break that down. Sounds like chess or tic-tac-toe.
Exactly. Perfect information just means fully observable. You see the whole board, everything. No secrets.
Got it.
Zero-sum is critical. It means basically what is good for one player is just as bad for the other. My win is your loss.
No win-win outcomes possible.
None. Pure competition. And we label the players max, trying to maximize their score, and MIN, trying to minimize Max's score.
Which in zero-sum means MIN is maximizing their own score, too.
Right. It's 2 sides of the same coin.
So for the AI, this all means it needs a really formal definition of the game, like down to the nitty-gritty rules.
Absolutely. It needs a digital rule book.
Yeah.
It needs to know the initial state, SCRO, how the game starts.
Right.
It needs to whose turn it is.
Yeah.
Legal moves from any state.
Makes sense.
Results A, what the board looks like after a move A from states, is terminals. How to know when the game's over.
Win, lose, or draw.
Exactly. And finally, utility, PS, the final score for player P in that terminal state test. Like +1 for a win, -1 for a loss, 0 for a draw, maybe.
It's like giving the AI the complete blueprints in the scoring system.
Without it, the AI can't even begin to play meaningfully. It's just noise.
Okay, so the rules are set. Now, how does the AI actually decide what move to make against this opponent who's actively trying to beat it? You mentioned minimax search.
That's the classic starting point. The core idea is that an optimal strategy isn't just the next move. It's a whole conditional plan.
A plan for every possible response.
Exactly. A contingent strategy specifying a response to each of MIN's possible moves. Anticipates everything. And we measure how far ahead it looks imply one move by one player.
And the key calculation here is the minimax value. What's that?
The minimax value of a state is the score for max that max can guarantee achieving, assuming both players play optimally from that state to the end.
Okay, assuming perfect play on both sides.
Right. So Max looks ahead and chooses the move leading to the state with the highest possible minimax value. MIN, conversely, looks ahead and chooses the move leading to the state with the lowest minimax value, from Max's point of view.
So it's this back-and-forth prediction. How does the algorithm actually compute this?
It's typically done recursively. The algorithm goes all the way down to the end states of the game, the leaves of the game tree. It calculates the utility there that backs up those values level by level. MIN nodes take the minimum of the values below them. AX nodes take the maximum.
That sounds incredibly thorough. Almost too thorough. What's the catch?
The catch is the complexity. It's exponential.
Right.
OBM, where B is the branching factor, average moves per turn, and M is the maximum depth.
And for something like chess?
For chess, B is around 35, meter read can be 80 or more ply. So 35 to the power of 80, that's roughly 10 to the 123 states.
Oh, okay. That's astronomical.
It is. The source puts it perfectly. The game tree is best thought of as a theoretical construct that we cannot realize in the physical world. You just can't search it all.
So even for games that seem manageable, the sheer number of possibilities explodes. This means minimax alone isn't enough. AI needed to get smarter.
Absolutely, and this leads to a really interesting nuance about optimal. Minimax guarantees the best outcome against a perfect opponent.
Right.
But what if your opponent isn't perfect? Maybe they make mistakes or don't have infinite computing power.
Does minimax still hold up?
It guarantees you won't do worse than the minimax value, but you might miss opportunities. The source gives this great example. Imagine a state where optimal play leads to a draw.
Okay, a guaranteed draw if both play perfectly.
But Max sees a risky move. If MIN responds optimally, Max loses. But maybe there are 9 other plausible responses from MIN, and all of those lead to MIN losing.
Ah, so if MIN slips up, Max wins big.
Exactly. If Max thinks MIN might not find that one perfect counter move, taking that 90% chance of a win might be much better than settling for the guaranteed draw. Optimal gets fuzzy.
That really challenges the definition. Okay, so brute force minimax is impossible. How did AI actually leap to playing complex games like chess at superhuman levels?
The first major breakthrough was alpha-beta pruning.
Pruning, like cutting branches off the search tree.
Precisely. Alpha-beta computes the exact same optimal move as minimax, but it's way more efficient because it eliminates subtrees that are provably irrelevant.
How does it know they're irrelevant without looking? That sounds like magic.
Yeah, not quite magic, but clever logic. It maintains 2 values, alpha and beta, during the search. Alpha is the best score Max has found so far that it can guarantee for itself on the path down to the current node. Think of it as at least this good for Max.
Okay, a lower bound for Max.
Right. And beta is the best score MIN has found so far that it can force Max down to. It's the lowest score MIN can guarantee. Think at most this good for Max.
An upper bound, so how does that help prune?
Well, imagine Max is exploring a move. If exploring down that path reveals that MIN can force a score lower than the alpha value, Max is already guaranteed elsewhere. Max knows it will never choose this move.
Because it already has a better guaranteed option.
Exactly. So it can just stop searching that entire branch. Cut. Pruned. Same logic applies for MIN using the beta value.
That's really smart. Does it matter which moves you look at first?
Massively. The effectiveness of alpha-beta is highly dependent on the order in which the states are examined.
Move ordering.
Yes. If you can somehow guess the best moves and search them first, you establish good alpha and beta bounds early, which lets you prune way more branches.
So how do you guess well?
Various tricks. Iterative deepening. Search shallow first to get a rough idea, then use that to order moves for a deeper search. Also, killer moves, moves that cause pruning in other parts of the tree recently, are tried first in new branches.
Clever heuristics.
Very. Good move ordering in chess can cut the effective branching factor from maybe 35 down to something like 6. Huge difference.
Wow. Any other tricks?
Transposition tables. Sometimes different sequences of moves lead to the exact same board position.
Right, a transposition.
The table stores the result, calculated for that position the first time it was seen. If you reach it again via a different path, you just look up the answer instead of recalculating. This can almost double the reachable search depth.
Okay, so alpha beta with good move ordering and transposition tables gets you much deeper, but often still not deep enough for the whole game, right? How do you handle cutting the search off early?
That's where heuristic alpha-beta search comes in. You decide on a maximum search depth, and when you hit it, instead of a terminal win-loss draw value, you use an evaluation function, eval, to estimate the position's value.
A heuristic guess.
A heuristic guess, yes, based on features of the state. Shannon called this a type A strategy. This eval function needs to be fast.
What kind of features?
For chess, the classic one is material value. Pawn 1, knight 3, bishop 3, rook 5, queen 9. Sum them up.
Simple enough.
Yeah, but you add others too, like pawn structure, king safety, control of the center. These features are often combined in a weighted linear function, though that assumes independence, which isn't always true. Modern engines use more complex nonlinear combos.
Right. But what if you stop the search right before, say, a queen capture? Your evaluation might be way off.
Good point.
Yeah.
That's the quiescence problem. The position isn't quiet. Your eval function is only reliable on relatively stable or quiescent positions.
So how do you fix that?
With quiescent search, when the main search hits its depth limit, if the position is unquiet, meaning captures or other forcing moves are possible, you extend the search just for those forcing moves until things calm down. Then you apply the evaluation function.
You search a bit deeper just to resolve immediate tactics.
Exactly. It avoids those nasty evaluation errors caused by stopping at a critical moment.
This leads to another issue, though, doesn't it? The horizon effect.
Yes, the horizon effect. This is tricky because the search has a fixed depth limit, its horizon. An AI might make moves that push an unavoidable negative event, like losing a piece, just past that horizon.
So it looks like it avoided the loss, but really just delayed it.
Precisely. It might even sacrifice material, like pawns, just to postpone the inevitable bishop capture until it's beyond the search depth. The AI thinks it's clever, but it's just making things worse long term.
How do you combat that?
One technique is singular extensions. If one move looks vastly better than all others at a certain point, you search just that move extra deep. This can help see past the horizon for those critical lines.
Okay. And what about forward pruning? You mentioned Shannon's strategies.
Right, alpha beta is backward pruning, proving branches irrelevant. Forward pruning, Shannon's type B, is riskier. It means deciding not to even explore certain moves from the start because they look unpromising.
So you might miss something good.
You might. It saves time, but risks errors. Techniques include beam search, only considering the top K moves at each step, or prob decutterate, which uses statistics to prune moves that are probably outside the alpha-beta window.
So with all these enhancements, alpha, beta, ordering, tables, heuristics, quiescence, extensions, pruning engines like Stockfish get incredibly strong.
Incredibly. Reaching effective depths of 30 ply or more in chess, far exceeding human ability. Deep Blue hit 40 ply in some lines against Kasparov.
Okay, alpha, beta dominated chess for a long time, but then came Go. Huge branching factor, like 361 initially.
And notoriously difficult to write a good evaluation function for. Position value is just so abstract.
So alpha beta struggled there. What emerged instead?
Monte Carlo Tree Search, or MCTS, a completely different approach.
Monte Carlo, like the casino,
Yeah.
involves randomness.
It does involve randomness, yes. MCTS largely abandons deep search and complex heuristics.
Yeah.
Instead, it estimates a state's value by running many randomized simulations of games starting from that state.
So it plays out thousands of potential game endings.
Millions, often. It runs these simulations or playouts or rollouts using the actual game rules to see who wins. The value of a state becomes the average outcome over all these simulations.
Does it just play randomly in the simulations?
It can, but effective NCTS uses a playout policy to bias the moves towards sensible ones, not just pure random. These policies are often learned, maybe using neural networks trained via self-play.
Okay, how does the whole MCTS process work? You mentioned a cycle.
Yeah, the standard MCTS cycle has 4 steps, repeated many times.
Okay.
1. Selection. Start at the root, move down the existing tree, choosing nodes. This needs to balance exploitation, picking moves that have looked good so far, and exploration, trying less visited moves to see if they're secretly good. The UCT formula is key here.
Exploit versus explore. Classic problem.
2. Expansion. Once you reach a leaf node in the tree during selection, you add 1 or more new child nodes representing unexplored moves from that position.
Grow the tree.
3. Simulation. From one of these new nodes, you run a playout using the playout policy all the way to the end of the game.
Get a result, win, loss, draw.
4. Backpropagation. Take that result and update the statistics, like win counts and visit counts, for all nodes visited on the path back up from the simulated node to the root.
So each simulation reinforces or weakens the perceived value of the moves along that path.
Exactly. Over millions of iterations, a very good estimate of move values emerges.
Now here's a pattern that seems surprising. MCTS worked wonders for Go, but then it started showing up and having success in chess too, right? Why? What are its advantages over the highly tuned alpha beta?
That was surprising to some. MCTS has key strength. It's less vulnerable to a single bad evaluation function error because it averages over many simulations.
More robust to heuristic mistakes.
Right. It handles enormous branching factors much better, and the simulation time scales linearly with depth, not exponentially like exhaustive search.
So even though alpha beta might be sharper in some chess positions, MCTS's robustness and learning capability proved really powerful.
Yes, especially when combined with deep learning for the playout policies and value estimates, like in AlphaZero. Sometimes you even see hybrid approaches now.
Okay, let's shift gears. What about uncertainty? Games aren't always perfect information. What if there's chance involved, like dice?
That takes us into stochastic games. Backgammon is the classic example. The game tree now needs chance nodes, usually shown as circles.
Representing the dice roll.
Exactly. Instead of MIN or max choosing, the dice roll determines which branch is taken. To handle this, you use expectiminimax.
Expectimimax.
Yeah, at max and MIN nodes, it works like minimax. But at chance nodes, you don't pick the best outcome. You calculate the expected value, the average outcome weighted by the probability of each dice roll.
So you average over the randomness. Does that make it harder?
Oh, much harder.
Yeah.
The complexity increases significantly because you have this branching factor in for the random outcomes at each chance node. The tree explodes even faster. OBMNM.
Yikes. And evaluation functions need to be different too.
Yes, they need to reflect the actual probability of winning or the expected score, not just relative preference. It's more demanding.
Okay, chance is one thing. What about hidden information? The fog of war. Partially observable games.
Now things get really complex. Partially observable games like Kriegspiel, blind chess, or poker are where players don't see the whole state.
So you don't even know exactly what the board looks like.
Exactly. You operate based on a belief state, the set of all possible actual states consistent with what you have observed so far. Planning becomes planning over this set of possibilities.
How can you possibly guarantee a win if you don't know the state?
You often can't guarantee it in the same way. You might need a probabilistic checkmate strategy, where you play in a way sometimes randomly that forces the opponent to eventually reveal information or blunder, rather than a direct forced mate that works in all possible states of your belief state.
Play randomly. Why would random play be optimal? That seems counterintuitive.
It is counterintuitive. But here's the key insight from the source. Playing any predictable, optimal strategy provides the opponent with information. If you're predictable, your opponent can exploit that.
Ah, so randomness keeps them guessing.
Exactly. Optimal play in partially observable games requires a willingness to play somewhat randomly. Sometimes a move that looks weak in isolation becomes strong because it's unpredictable and your opponent hasn't prepared for it. It's crucial for things like bluffing and poker.
Which means you can't just average over possible futures assuming you'll know everything later.
Right, that's the averaging over clairvoyance fallacy. It undervalues gathering information now or concealing your own. Programs like Libratus for poker had to tackle this head-on, using abstraction and adaptation.
So we've seen these incredible leaps, but what are the remaining hurdles? What are the limitations of even these advanced search algorithms?
Well, alpha beta is still sensitive to evaluation function errors, especially if they compound. And both alpha beta and MCTS are kind of exhaustive at each step. They calculate values for all legal moves. Even when one move is obviously forced or clearly the only sensible option, that wastes computation.
Which sounds like they lack common sense. Or maybe meta-reasoning?
Exactly. Meta-reasoning, reasoning about reasoning, deciding how much effort to spend thinking about which move. MCTS does a bit of this with exploration exploitation, but it's not truly optimizing the value of computation itself.
And they still think move by move, mostly, not at a higher strategic level.
Largely, yes. Humans can set abstract goals like trap the queen and plan towards that. Current AI reasons more directly about the sequence of moves and resulting positions, less about those high-level conceptual plans.
Looking back at this whole arc, from Samuel's checkers to AlphaZero, what's the biggest, most surprising pattern you see?
For me, it's the undeniable shift away from relying on human experts to program the strategy towards AI learning it entirely through machine learning from self-play.
The AI teaching itself.
Completely. We went from Samuel learning evaluation weights to Deep Blue using heavily human-tuned heuristics to AlphaGo combining search with deep learning trained on human and self-play games to AlphaZero learning chess, Go, shogi entirely from scratch. No human games, no opening books, just the rules and playing itself millions of times. It reached superhuman levels with strategies humans hadn't conceived of.
And then MuZero didn't even need the rules up front.
Right. MuZero learned the rules and how to play just by experimenting. That progression is staggering. It's a move from encoding human knowledge to genuine automated discovery.
We've covered a lot of ground today, from the basic max versus MIN conflict through minimax, the efficiency of alpha beta, the different philosophy of MCTS, and into the complexities of chance and hidden information.
Yeah, and it's fascinating how mastering games pushed AI to develop techniques for handling complexity, uncertainty, and incomplete information problems that mirror the real world in many ways.
That shift from human programming to self-learning feels like the dominant pattern.
It really does. It suggests AI might find solutions we simply wouldn't think of.
It makes you think of that Gary Kasparov quote after AlphaZero's success, doesn't it? About chess being shaken to its roots. But that being just a tiny example.
Hidebound disciplines like education and medicine will also be shaken.
Yeah.
Powerful stuff.
So the final thought maybe is, if AI can redefine optimal play and discover completely new strategies in the closed world of games just by playing itself, what surprising, maybe even counterintuitive approaches might it uncover when we point it at much messier, open-ended real-world problems? What might it teach us about optimal strategies in areas we thought we understood?
That's the really big question, isn't it? Something to definitely mull over.